right, welcome back to West Virginia. Here we are in our great state. Are you ready for Joke of the Day? Of course you're ready for Joke of the Day because it is the best way to start the day, isn't it? Are you ready? Let's do it. So what do you call an alligator in a vest? An investigator. Okay, let's investigate inverse functions. Okay, so an inverse of a function, we've got a great definition sitting here. The inverse of a function is the unique relation that is formed by interchanging the x and y coordinates of the ordered pairs. That's what it comes down to. In a nutshell, you interchange your x and your y coordinates. That's the biggest thing you've got to remember about inverses. That drives everything we're going to talk about inverses. Now, once you've determined that, yes, I am going to have an inverse here, then we give it a new symbol. Now, remember, this is saying the inverse of a function. So I'm starting off with a function that has this notation right here. And so to denote that this function has an inverse, I'm going to use something similar to this. But what I'm going to do is I'm going to put a -1 up in there. Now that -1 is not an exponent. And remember, the laws of exponents said that if you had a -1 in the exponent, that would mean flip. It would mean take the reciprocal. This does not mean the reciprocal of f. By no means. That is not at all what it means. This is simply notation. So when you see this notation, you should read it as f inverse. And it simply means what I'm going to see with this is the inverse of this function. Again, not reciprocal. This is not an exponent at all. So in this example, it says, here's my f function. It is this string of ordered pairs, and I want to find the inverse. Remember, this means f inverse. And in order to find that inverse, like we said, all we're going to do is interchange the x and y coordinates. So that means my f inverse then is simply going to say, take this ordered pair, flip the x and the y. So instead of 5, 1, it becomes 1, 5. Take this ordered pair, flip the x and the y. So instead of 10, 2, it becomes 2, 10. Same thing here. Flip that ordered pair. So instead of 15, 3, it becomes 3, 15. And flip the ordered pair on this last one. Instead of 24, it becomes 4, 20. And there is my inverse function. So like I said, the premise of everything we're going to talk about in this lesson is to interchange the x and the y coordinates. So now let's take that idea and let's figure out, okay, how are we going to determine if we have an inverse? So if your function has a 1-to-1 correspondence, then that inverse exists. 1-to-1 correspondence. So now we have to figure out, okay, what is a 1-to-1 correspondence? The 1-to-1 correspondence of a function is when your function in which each x has only one y and each y has only one x, looking like this right here. Now, remember, we talked about functions themselves, and we said, how do you determine whether or not you have a function? And I said, you're going to burn this picture in your brain that when I have the same x going to 2 different y values, I said, put a great big X over that, that is not a function. And I said, everything else is a function. And when I said everything else is a function, that could mean 1 y going to 2 different x's. Even though that's kind of weird, that's okay. That's a function. And I said, better than that, what if I had 1x going to 1y? That's a function. Or reversing that, which is this case right here, 1y going to 1x, vice versa. This is even better than a function. This takes it a step further. This says, ooh, I've got a 1-to-1 correspondence. So like I said, what happens here with the 1-to-1 correspondence is it takes what is a function and moves it a step further. So once we recognize what a 1-to-1 correspondence is, we can take our functions and we can identify, okay, is this function the type of function that has a 1-to-1 correspondence? Because if it does, then I know that that inverse is going to exist. If I have a 1-to-1 correspondence, the inverse exists. So how do I take a function and determine if there is a 1-to-1 correspondence? What we use is what's called the horizontal line test. Now that should sound familiar because we had a vertical line test to determine whether or not we had a function. Remember, that vertical line test said, hey, if I take this function right here and I drop a vertical line through it and that vertical line hits 2 or more times, this is not a function. That was what the vertical line test did. If it hit once, it was a function, perfectly fine. But if it hits 2 or more times, then it's not a function. Similar idea with the horizontal line test. The only difference, you're going to draw a horizontal line instead of a vertical line. So if you draw that horizontal line and it passes through only once, then you definitely have a one-to-one correspondence. It is a one-to-one function. But if it passes through 2 or more times, in other words, more than 1 point, similar to the vertical line test, this is not a one-to-one function. So the rules are very similar. The only difference is whether you draw a horizontal line or a vertical line. Vertical line is for functions. Horizontal lines are for one-to-one correspondence. So let's take a look at these 2 examples. In each of these examples, I already know that they're functions. If I drop a vertical line through here, it's hidden once. Vertical line through here, it's hidden once. Vertical line right through here, it's hidden once. I know this is a function. I need to determine does it have a one-to-one correspondence? Because if it does, it has an inverse. So what I'm going to do is utilize the horizontal line test. The horizontal line test says, hey, let's draw a horizontal line in here. Hits once there, hits once there. Aha! This one is not a one-to-one function. So an inverse is not going to exist on this one. Now, let's take a look at this one. Once again, I already know it's a function. Drop a vertical line through here, hits once, here hits once, here hits once, here hits once. Even if I drop that vertical line right through here on that y-axis, it's not hitting at all. But hey, it's not hitting more than once, so this is definitely a function. But now I need to determine, is it a one-to-one function? So now, looking at the one-to-one function idea, what happens here is, I'm going to say, let's drop a horizontal line, hits once, horizontal line here, hits once, here, once, here, once. Even if I drop it right here on that x-axis, it's not hitting at all, but that's okay. So the fact that it's hitting only one time, this is definitely a one-to-one function. So like I said, this is how, if you have a graph, you are going to determine whether or not you have a one-to-one function. Because if you have a one-to-one function, then the inverse is going to exist. So now let's move ourselves a little bit further and say, okay, well, now that I'm talking about whether or not an inverse exists, how do I get that inverse? Well, there are 3 different formats that we can follow, and I'm going to get this out of here, but I'm going to keep this definition up here of being able to swap out or interchange those x and y coordinates. That's going to drive everything that we talk about at this point, so I'm going to leave it up there. So like I said, in order to say, okay, I know an inverse exists, now how do I get it? Let me switch colors on us so we don't get this mixed up. To find the inverse of a function, that is n. Now there's 3 different forms your functions can take. The first form, like we said before, was simply a bunch of ordered pairs. Ordered pair form. And we said, okay, if it's in ordered pair form, we said, well, all we have to do is interchange those x and y coordinates, like what I just erased, x and y values, or x and y coordinates. That will create the inverse of that particular function that I started with. So if I have ordered pairs, it's very easy to do. Now, what if I have a graph like we just saw? Now, if it's in graph form, what you're going to do is you're going to reflect this, your graph, over the line y equals x. Because the line y equals x, if you reflect your points over that, that interchanges your x and y coordinates. Let's go back and look at these examples. Now, this one, remember, it was not a one-to-one correspondence, so the inverse isn't going to exist. I'm going to look at this one here, and let me just redraw it because we got a lot going on there. It's going to be very difficult to see. So remember, it started like this and like this. Now, my line y equals x goes right through like this. And the reason I'm going to reflect over this is, let's say, for instance, this point right here, let's say that that was the point 4, 1. If I needed to interchange the x and the y, then it would become 1, 4. Well, 1, 4 is going to sit right up here And take a look at this. If I reflect this over that line y equals x, this point goes right up there. And if I reflect this down here, that point goes right down there. And the same thing's going to happen over here. What if I call this point right here a -5, -2? And if I interchange the x and y coordinates, then it becomes a -2, -5. Well, -2, -5 sits down here. And you can see, sure enough, as I reflect this across that y equals x line, this part comes right down there, this part comes right up there. And so that's why if you have a graph, and you already know that it has a one-to-one correspondence, in order to create the inverse, you're simply going to reflect it across that line. So the inverse of this part will flip up here like this part will flip down here like this part will flip down here, and this part will flip up there. So basically it'll be itself, which does not always happen, but that does happen in this particular case. Now the third option is, what if I start off in equation form? Well, if I'm in equation form, what happens is we need to recall that we have an f of x. And we need to remember the whole idea is interchange those x and y values, swap out x and y. But if I have an equation, I don't have a y, I have an f of x. So what I need to do is I need to first change that f of x to y. Because once I change it to y, then I can swap out my x and my y. And that will be the next step, would be to interchange the x and the y. But once I've done that, now my equation will have an x by itself. Well, that's not what I want. I want the y by itself. So I will solve it for y. But then I want to get back into that function notation. Because when I'm talking about inverses, I'm talking about inverses of functions. So I want to denote functions. But I don't want to go back and once I've solved for y and have that y by itself, I don't want to call it f of x because that was my original equation. But if I want to keep in function notation, then what I'm going to do is I'm going to write that y as f inverse of x. Or if I started off with a capital F, because this is lowercase f, it would be capital F inverse of x. But either way, I'm replacing the y with that function notation, just being very careful to put that inverse notation in there to remind me, oh, this isn't the original equation, this is my new one, the inverse that I created. So let's take a look at some examples, and I've got 3 here where we are going to take the original equation and we are going to create the inverse equation. And then once we get through these examples, we're going to verify that these truly are inverses of each other. All right, enjoy that beautiful West Virginia scenery behind me as I get this board cleaned up and ready to go. So, keeping with, this is step number 5 under the equation form. And so these examples, what we're going to do in each of these is we are going to write the inverse of each. Write the inverse of each of the following. Okay, so in my first example, I have f of x equals 4x plus 6. Now, like I said, in order to, and basically when it comes to inverses, all you really have to remember is exchange the x and the y. That's really what it comes down to. Exchange the x and the y. But I don't have a y here. So I go, oh, that's easy to fix because I know f of x acts like a y. There's my y. So then I go, okay, now I can swap them out. This becomes the x, and this becomes the y. And so now I go, okay, but I have to solve this for y. I have to get the y by itself. Well, if that's the case, I'm going to subtract my 6, and then I'm going to divide by 4, keeping in mind that I'm dividing the entire side by 4. Now, I could just call it x minus 6 over 4 equals y, but most textbooks, most instructors want us to go ahead and separate that out and call it 1/4 x minus 6 over 4 reduces to 3 halves. You'll see why in a minute, why that helps. Actually, well, either way is perfectly fine. But I can leave it like this, I can leave it like this. Regardless though, I definitely want to create it into function notation. Now here's where I said I don't want to call it f of x because f of x was this. So I'm going to call it f inverse x. So f inverse x will be 1/4 x minus 3/2. Or in this case, f inverse x will be x minus 6/4. And either one of those is perfectly fine. Now let's take a look at another example. This one I'm going to say let's start off with x squared minus 1. And once again what I'm going to do is create the inverse. Now remember, inverses mean swap x and y. But I don't have a y here. And I go, that's right, f of x acts like a y. So here it is. And now I'm ready to swap them out. This becomes the x, this becomes the y. And I go, okay, now I need to solve it for y. So I'm going to add 1 to the other side. And at this point, to get that y by itself, I need to take the square root. So I'm going to take the square root here, take the square root here. And that will give me square root of x plus 1 equal to the y. And remember, what I need now is to put it back into function notation, but I don't want to call it f of x because that was this one. So I'm going to say this is f inverse of x, and that's going to be square root of x plus 1. There's my inverse. Okay, let's do one more, and we'll flip this board around, and let's go back and put that right up in here. And so this one, where am I? Is C. And so I've got f of x equal to, actually let's put that down a little bit lower because I'm going to erase up here and use it in a minute. Here we go. F of x equal to square root of x minus 2. So now in order to create that inverse, remember what inverse means, swap x and y. That's all it is. But I don't have a y in there. So I'm going to make this the y because that's what f of x means. F of x just simply stands for a y. Now I can exchange them. Call this the x, call this the y. And now I'm ready to solve for y. But that y, you'll notice, is buried underneath that radical. So in order to get it out and free it from the radical, I got to get rid of the radical. The only way to do that is to square the entire side. And remember what you do to the side. So I have x squared, and then over here squaring and square rooting cancel each other out, and I have a y minus 2. And now to get that to get the y by itself, I'm going to add that 2, and that gives me x squared plus 2 equals y. And now I'm just going to put it back in function notation, but I'm not going to call it f of x because that was the original. I'm going to call it f inverse x, and f inverse is going to be x squared plus 2. There's my inverse. So, hopefully you're seeing that to create an inverse is not that hard, honestly. If you have ordered pairs, just swap the x and the y on every single one of those ordered pairs. If you have a graph, just reflect it across that y equals x line because that allows you to swap out your x and y coordinates. And if you have an equation, all you got to do is turn your f of x into a y, swap them out, solve for y, and then put it back in function notation. Well, now that we know how to create those inverses, let's say that we have a couple of equations that we are being told they are inverses of each other, and we need to verify this. We need to know, are these really inverses? Well, the way that you verify that, this is why we did our composite functions back before. In order to verify that you have inverses, f and g are inverses or inverse functions if and only if. So in other words, it's got to be this. When I take my original function f and I put g inside of it, in other words, f of g of x, the composition or the composite function f of g of x, and I do the reverse and I take my g function and put my f function inside of it, in other words, g of f of x, when I do that, and in both cases I get an x as my result, then they truly are inverses of each other. So you take your f function, plug it into g. Take your g function, plug it into f. Both cases, if it results in an x, you got inverses. So let's double check the inverses that we just created on these three examples, and let's prove that they truly are inverses of each other. So let's take this one, and I'm going to check that they really are inverses. So remember what that means is I'm going to take my f function, and I'm going to put my inverse function inside of it. I better get an x. Well, here's my inverse function that I'm going to plug in here. I'm going to take all of this and plug it right there where that x is. So instead of 4 times x, it's now 4 times all of this, minus 3 halves, plus 6. Now you know you need to distribute that 4 through. 4 times 1/4 cancels, and I get an x. 4 times negative 3 halves, well, 2 goes into 4 twice. 2 times 3 is 6. So I get a negative 6 plus 6. These cancel. Sure enough, I get my x. Now, if I wanted to use this instead of this one, then it would be 4 times all of, because I'm plugging it into here, 4 times all of this over 4. But here again, these will cancel, and I'm left with exactly this right here. X minus 6 plus 6. So either one of these works out just fine. Now, I need to check, though, taking my inverse function and plugging f of x into that. So I took my inverse and plugged it into the original. Now I need to take the original and plug it into the inverse. So instead of 1/4 times x, it's 1/4 times all of this, 4x plus 6, and then don't forget to subtract 3 halves after that. Now you know to distribute your 1/4 through. 1/4 times 4x is just x. 1/4 times 6 is 6 over 4, but that simplifies to 3 halves. And 3 halves minus 3 halves, sure enough, I do get an x. And again, if I chose to use this one instead, then that means that I'm going to plug this in here. And when I do, that 4x plus 6 will go right here. So I'll get 4x plus 6 minus 6 over 4. 6 minus 6 cancels, and I get a 4x over 4, which sure enough is just an x. So I have verified, yes, these really are inverses of each other. Because when I plug the inverse into the original, I got an x. When I plug the original into the inverse, I got an x either way. Now, let's take this one and verify that what we got for its inverse truly is an inverse. So once again, that indicates I'm going to take my original function and put the inverse inside of it. So here's my original, here's the inverse. I'm going to take this right here and plug it right there where I see an x. So that means I'm going to take this and I'm going to square it and then subtract a 1. Now squaring and square rooting cancel each other out, so that's completely gone, and I'm left with just an x plus 1 minus 1. 1 minus 1 is 0, and I'm left with just an x. So I'm feeling good, but I need to verify the other side. So to verify the other side, I'm going to take my inverse and plug my original in. So I'm going to take this original, plug it here into the inverse. So instead of square root of x plus 1, it'll be square root of this plus 1. Now here, negative 1 plus 1 cancels. I'm left with square root of x squared. Squaring and square rooting cancel each other out. I'm left with x. So I got an x in both cases, taking the inverse and plugging it into the original, taking the original and plugging it into the inverse. Both times I got an x. That tells me, yes, these really are inverses of each other. In other words, pat yourself on the back. You did a good job. You got the right answer. Now, last one. Let's verify that these really are inverses of each other. So once again, what that indicates is I'm going to take my inverse and I'm going to plug it into the original. So inverse plugged into original. Here's my inverse. I'm going to take all of this and plug it right there where I see an x. So instead of square root of x plus 2, it's going to be square root of all this minus 2. Now the 2 and the 2 cancel. I'm left with square root of x squared, feeling kind of familiar. This is kind of what it looked like before. And square root of x squared, they cancel each other out. I'm left with an x. And now I'm going to verify the other side and say, all right, let's take the inverse and let's plug the original in there. So I'm going to take this original right here and plug it in right there where I see that x. Now notice what that means is I'm going to take this and I'm going to square it, and then I'm going to add a 2. And once again, squaring and square rooting cancel each other out. I'm left with x minus 2 plus 2. And negative 2 plus 2 cancels, and I'm left with just an x. So in both cases, taking that inverse and plugging it into the original, I got an x. Taking the original, plugging it into the inverse, I got an x. So you can pat yourself on the back and go, hey, this was the right answer. And that's beautiful, that once we get these inverses, we can check and make sure that we've really done our work correctly, because we can plug it back in and verify that they truly are inverses of each other. Now, I want to give you an example, because every one of these worked, and I want to give you an example of something that really is not an inverse of each other. So let's take this and we'll call this, let's see here, I've lost track of what I'm doing here, so we'll just call it 5. So an example of non-inverse functions. Because you may be thinking, well, from the looks of it, everything's going to be inverses of each other, because that seems to be happening all the time now. But let's take this case. F of x is 3x plus 2, and my g of x is going to be 1/3 x minus 2. Now it feels like they'll be inverses, because after all, if I take a third and multiply it to 3, they'll cancel out. And a 2 and a negative 2, they seem to cancel each other out. So it kind of feels like they're going to be inverses of each other. But let's check and see what happens. So remember, I need to verify. I need to take my original, plug the inverse in. So I'm going to take, this time I don't have, better not put inverse f. I better put g of x. So I apologize for that. All right, take one function, plug it into the other. So I'm going to take this g, plug it right in there. Better come up with an x. Now when I distribute that 3 through, I get x minus 6 plus 2, giving me x minus 4. Well, frankly, I could call it quits right there, because I can see immediately, oh, I'm not getting an x. I'm done. Even if plugging in the other direction would give me an x, I have to get an x in both cases. So this tells me no way they are not inverses of each other. So hopefully that helps explain inverses. And like I said before, big thing is just remember, swap your x and your y. That's about it. Easy enough. I hope it helps. Have a great day.